Yeah, so anyone who is not familiar with RFG, this RFG stands for Research Focus Group, and it has been in conjunction with AbGradCon for 5 years now, is that right? Anyway, so this is an opportunity for participants at AbGradCon to get an experience writing research grants. So these are grant proposals in the style of NASA proposals, NSF, DOE, that kind of thing. And it's a unique opportunity you've seen the diversity of our areas of research already at this conference, and in just a short weekend, the RFG event is a Friday through Sunday morning. Students come in and write a full research proposal from the science to the budget to the timeline, everything in just a weekend, and try to bring together and incorporate everyone's different backgrounds. So it's perhaps a little different from what you might experience in the future, but you still get that great firsthand writing experience. So with that, I'd like to introduce the winning team from this year's RFG, Apar Prasad, Sarah Gillett, and Arsham Shalari, and they will talk about methane sequestration and recovery.
So I'm Arsham Shalari. I'm here to talk about development of a solid phase sorbent material for methane recovery filter. I'm here with Sarah Gio and Apar Prasad. So to motivate the talk, I'm going to talk about global warming for a few slides. What you're seeing here is the surface temperature estimates from the Intergovernmental Panel for Climate Change. So the shaded regions are basically one standard deviation from the mean, and then the gray bars you see on the side are different scenarios that they have predicted. So this orange line is basically if we could freeze the greenhouse gas levels at the 2000 level, year 2000 level, and these are the different projections from different groups. And regardless of if we could end up here or here, neither scenario is really pleasant. A consequence of this, to make it a little more understandable for somebody who doesn't know, what a 2 or 3 degree change would mean, is the difference in sea level. So this is this dashed line is year 2007, and the shaded region here is the different scenarios that you're gonna see. So the best case scenario is 20 centimeters sea level, global sea level rise, and the worst case scenario is 50 centimeters change, which is, as all you might agree, is very dangerous. Part of Miami, part of Manhattan will be underwater, along with Venice and many cities. So this is the composition of greenhouse gases. Most of it is carbon dioxide, which gets a lot of attention, appropriately so. But there is this 14% methane, which is important because methane is 25 times more potent as a greenhouse gas than carbon dioxide. And the problem we're having these days is that because of the global warming situation we are in, a lot of the natural gas industry and the general public prefer natural gas compared to coal because they think it's a cleaner source of energy. Where the problem happens is that when you have a lot of activities around natural gas, there's a lot of leakage. So in power plants and natural gas production, there is between 1 to 2 or 3% leakage, and that 2 or 3% leakage times 25 times being more potent is a big problem. So here's a breakdown of where all the methane emission sources are. And the part that we are focusing on is the natural gas and petroleum systems. There is a lot of capture mechanisms for landfills and agricultural sources, but not much has been done for petroleum sources. So with that, I will give it to Sarah to talk about the actual part.
So the basic overview of what we want to do here is have a solid phase filter that we can flow a stream of air over, which is probably methane rich because we're targeting these leakage sources, and have it selectively bind methane while still passing through the other components of air. So the requirements for a filter such as this is that you're going to need a strong binding of methane. And the challenge of that is that methane is a nonpolar molecule, and so you're not going to have very strong interactions with this solid phase. And so our approach to maximize those interactions to have a strong bonding of methane is that we're going to employ nonpolar species on this filter to sort of enhance the nonpolar interactions. We're also going to incorporate some porosity in there to enhance the methane kind of sticking to that surface. Okay, so the second requirement is that we want to be able to have a fast flow of air through this filter. So in order to do that, we're going to have a high selectivity of it binding methane versus the other components of the gas. In order to do that, we're going to target specific pore spacing of this solid sorbent material. And the reason for that is that there's been studies that have shown that if you take two methane molecules and you bring them together, there's a certain point where they have a minimum of energy. That's the distance between them. And so if you have pores that are spaced right around that minimum of energy, which is right around 4.2 angstroms, then you're going to be able to maximize the binding of methane versus N2 or CO2. And the third component the third requirement for this kind of filter is that we want it to be reversibly binding methane. So not only do we want methane to attach, but we want to controllably then be able to release it so we can recover this methane as a usable fuel. And for that, we're going to look at things like changing the temperature and the pressure of the filter system. So this is kind of a very general schematic of what this kind of filter would look like. So you'd have an input of air where the methane is adsorbed onto the filter, and the rest of the air flows out, and then we would change the conditions of temperature or pressure, and the methane would release into a second output where we could store it, or it could be stored and then transported. And we have three components to this approach. The first is investigating promising sorbent materials, so this would be kind of the wet chemistry part of this project. The second is more on the theoretical side of things, so we look at the thermodynamics of binding and airflow. And the third is on the mechanical engineering side of things, actually starting to look at what goes into building a prototype for this filter. So all of the purpose of having an approach like this is threefold. Is first of all, the three of us are coming from very different backgrounds, so each of these plays to one of our strengths. I'm a materials chemist, Apar is a chemical thermodynamicist, and Arsham is a mechanical engineer. So our interests and our expertise fit right into these three different models. The second advantage of this is that this is something that hasn't really been approached before. Methane filters isn't something that's really out there. And so we're starting from first principles, and we want to attack it from all different sides. So we're not saying that we're going to be able to produce a commercial product by the end of this proposal, but we want to be able to lay a good foundation, not only on the chemistry, but also in the thermodynamics and the modeling, as well as start to thinking about the engineering of things. So the thermodynamics will help us then identify more promising chemical materials. Starting to look at the engineering will then help inform our modeling systems. And as we look at the engineering, we'll be able to see what kind of constraints there are for developing these materials. So eliminate any obstacles that might show up later on down the road. And the way we're going to start going about identifying a sorbent material, the chemistry part of this, we're going to start with the principles of gas chromatography. So gas chromatography, if you're not familiar with it, is a separations technique. The way it works is you input your sample using a carrier gas into this column, which is packed with a solid phase material, something like this polymer here, which has a silicon oxygen siloxane backbone and then these long N-octyl hydrophobic groups coming off of it. And so your sample, as it goes through the column, will be in one of two phases. So it'll either be adsorbed to the solid material, or it'll be in the carrier gas, which is flowing through the column. And the amount of time that it spends adsorbed versus in the carrier gas, that'll determine the retention time of your molecule, and that's how you can get separations of different molecules with different interactions with the adsorbing material. So what we want to do is take this principle and then just really enhance the adsorbing part of this, the adsorbing phase of the samples going through the column. And so we're really gonna play around with the we're really going to play around with the groups that are coming off of the backbone and try and see if we can enhance the interactions of the methane molecules with those groups. The other thing we're going to look at, as I mentioned, is pore spacing, and the way that you can do that is by playing around with the branching, the cross-linking of these polymers. So studies have shown that the amount of cross-linking that you do will change your pore size. There's been some body of research on hydrogen storage, which they've shown, with cross-linked polymers, you can store hydrogen in the pores of those materials. So that's kind of the chemistry side of things, and Har will tell you about the thermodynamics.
And I have 23 seconds left. So overall, we want to make a device which is thermodynamically feasible, which means that the overall Gibbs free energy change of the process has to be negative, because we want to have the system do some useful work and not require useful work. And the thermodynamics of CO2 capture has been studied extensively. This is from, and the way you study this is by basically studying the Gibbs energy demands and Gibbs energy supplies. On the left, we have the Gibbs energy demand for CO2 capture. As you might note, the numbers are positive. And the Gibbs energy supply basically came from hydration. Of course, we are working with methane instead of and not carbon dioxide. So while our Gibbs energy demands would be same, our supply has to be different, and that basically comes from the change in temperatures and pressure, or surface thermodynamics of helium binding. So to sum it up, we need to maximize methane capture, minimize methane consumption, power consumption, so that we have a negative carbon footprint, which is actually positive, and set up the right inflow with the right amount of methane concentration and right temperature, humidity, pressure to maximize our efficiency, and test for greenhouse gas balance between the operation side. So we have a very ambitious project over here, and so there are going to be challenges on the way, but we've tried to cover most bases. But it's something that needs to be done in this time of these times of anthropogenic climate change, and the rewards are huge. So we look forward to investigating this. Thanks. Questions?
We can take a question or two if anybody has a question about a very ambitious proposal. I think everybody may be really hungry for dinner.
All right. Okay.
All right, well, let's thank our RFG participant winners again.